So you can look at those to check what you did on your homework and how you did on the homework quiz. And just to go ahead and let you know, your midterm exam will be in class and it will be largely based on your homework. So that's one of the reasons I'm giving you the homework solutions, is so that you'll have this tool to check your solutions with and then also to study by. Okay, so I'll largely just draw the midterm exam material from this homework. Are there any questions before we get going today? Good question.
When about the midterm?
That's an excellent question, and I will give you the answer on Thursday. I haven't decided yet. Usually it's kind of based on where in the material we are, but we're actually moving a little bit quicker because we don't have these 15, 20-minute homework quizzes in class, which is good because last time I taught this class, I didn't get through all the material I was aiming at. This time, I think not only will I get through all that material, but I'll get a couple of extra topics in there, which is sort of the evolution of this course. But anyway, at any rate, I'll check and see my progress, and I'll let you know on Thursday. Might be a good idea to email me that question again, though, so it's flashing in my face. I have a hard time with memory sometimes. All right, so it is time to step up our treatment of vectors to that thing which seems to make so much sense, and an idea that you were introduced to pretty much the first day you were introduced to vectors. I want you to notice, though, how much we've done without it. We have done a lot without an inner product, right? Never at any point have I told you how to multiply two vectors together, okay? Okay, so there's a lot in the basic definition of vectors that you could do without this inner product, but of course, introducing the inner product introduces a lot of powerful stuff, so that's what we're going to turn to today. So to get started, let me give you a generic definition for an inner product. It might look a little different than what you're used to, but that's something you should be used to in this class. Things are a little more general than the and the concrete examples used before. Dang it. Okay, it's fine. All right, hopefully this one works. If this doesn't work, we're going home. Yes. An inner product is a real or complex an inner product in a real or complex vector space is a scalar valued function of the ordered pairs. This is a word which you're probably not used to when thinking about the dot product, but you'll see why it's important in a moment. Ordered pair of vectors x and y such that the following holds. 1, the inner product of x and y, which we're going to notate just by a set of brackets, is equal to the inner product of the reverse order complex conjugate. Okay? This is where order becomes important. If everything is real, then starring it doesn't do anything, and you can swap the order freely. If they are complex, then you can't swap the order without starring them, complex conjugating them, okay? That's why the order matters for the case of complex. And then obviously we have these linearity conditions, okay? Where the coefficient of anything which is on the left-hand side of the inner product, the coefficients are going to come out starred. So this is going to become alpha star xz plus beta star yz, where alpha and beta are just scalars, as usual. Or you could say they're the elements of the field over which the vector space is defined. And then last but not least, if I take the inner product of a vector with itself, this is greater than 0 for any x. And if the inner product of a vector with itself is 0, this tells us that the vector itself is 0. Okay? Now this is just a definition, so all of this is something which we just accept, and then we can, of course, break from there and go on. This third condition might, yes?
Do spinners not make a vector space?
Spinners form representations of rotation groups and the Lorentz group and so forth and so on. They do, in a sense, form a vector space, but we're gonna talk about spinners. So spinners are just a representation of a linear transformation, or sorry, of the rotation of the Lorentz transformation group. Are you worried about condition 3?
I was thinking of condition 2.
Condition 2. Why are you worried about condition 2?
Never mind. Continue.
Well, no, condition 3 is the one that might alarm some of you. How many of you have done relativity? Okay, in relativity, you know you can take the inner product of something with itself and get a negative number. Okay, remember ds squared, that's the infinitesimal displacement as a vector dx mu, and then you do dx mu. That can be positive, negative, or 0, depending on whether it's light-like, time-like, or space-like. Well, that is a difference between this definition of an inner product and the definition of an inner product that we use in relativity, and we'll come to that in time. We'll talk about the vector space geometry of special relativity as opposed to Euclidean space later. Okay, so this definition can be relaxed, especially for the case of relativity. Okay, if the vector space is real, then this leads us to what is often referred to as Euclidean. And if it's complex, that is, it's a Euclidean inner product, and if it's a complex vector space, then it leads to a unitary. Okay? Now, with this definition in hand, we've got some very, very familiar things, which I'll just quickly write up. First of all, we can define the length of a vector. As a square root of the inner product of the vector with itself. And notice, this is the reason why we want the star on here. Because if we have a complex vector and we take its inner product, but we're starring it, okay, then that means it must be real, and therefore the length of even a complex vector is real. And that's important, okay? We can also define the angle between any two vectors, and this is true in any number of dimensions. It's just the inverse cosine of the inner product of the vectors divided by the magnitude of each vector. We can also define orthogonality. If the inner product between two vectors is 0, then x and y are orthogonal. And lastly, we can define orthonormality. That is, the set x1, x2 up to n is orthonormal if the inner product of xi with xj is just the delta function, I, j. For any I and j. Okay. Right. Now, a lot of this should make sense from the context in which you've when you first saw the inner product, and that's just the dot product between vectors. But it turns out this is applicable to more general situations, and we'll see some examples. So let's just go ahead and cut to some examples. So one, for Rn, this is the good old dot product. So obviously we can take a vector and we can isomorphically map it to an n-tuple. If we're in R2, we can map it to a two-tuple. Sorry. At any rate, so we'll just list the coefficients. So this is just the coefficients, and then to write out the actual vector, it would be A times the first basis vector plus B times the second basis vector. But we can ignore those basis vectors and just do everything in terms of n-tuples and then matrix multiplication. That's the simplification that we've learned. And then we might have a second vector, YCD. Whoops, that's a D. In which case, XY just turns out to be AC plus BD, which of course is the same as YX because everything's real. Okay? So of course in matrix language we would call this AB times CD. So there's a certain sense in which to do it matrix using matrix multiplication. The first thing we keep as a row vector, and the second thing we turn into a column vector, and then we just use matrix multiplication. Okay? Pretty straightforward. For complex case, okay, now these terms can be complex, and so what we find is that xy is A star C minus B star D, which is the same as yx star, okay? Where we can imagine this is A, B star, C, D. Okay? Everybody on board? Good. Now, in 1 and 2, so in these two definitions, I want you to bear in mind something. We're using a set of basis vectors that are essentially orthonormal. They're orthogonal and they have unit length, okay? That is, and I'm gonna be really explicit about this. This is gonna be really kicking it back to Calc 1 or 2 or Physics 100. So, you know, if we do x is a I hat plus b j hat, and y is c I hat plus d j hat, then the way that we understand the inner product is basically multiplication of these two bilinear things. So we have a times c I hat dot I hat plus a times d I hat dot j hat plus b times c j hat dot I hat plus b times d j hat dot j hat. But clearly, because these are orthonormal, this is 0, this is 0, and because it's normalized, this is 1, and this is 1, so we get AC plus BD. Does that make sense? I mean, that's obvious, okay? Now, we could make this something more complicated in a couple of ways. First and foremost, we could say, all right, so if I take x equals AB and y equals CD over the reals, then I could say, all right, fine, I'm going to take the inner product to be A, B, and then in between it's going to be a matrix, which is not the identity, times CD, and this is going to give me AC plus 2BD, which is of course the same as y and x. Okay. So this is obviously a variation on the definition of the inner product. It's not this standard Rn example. All right. Where this thing right here is playing the role of something which I know you've seen if you've ever taken my general relativity course. Hey, the metric, okay? Now we won't do a lot with that when we're going through the book, but I will give you some discussion of the metric in due time. But one way that you can think of the metric is that it's basically taking the second vector, which is part of the basis. You've got two vectors in the basis. It's taking the second vector in the basis, and instead of giving it a length of 1, it's giving it a length of root 2. Okay? So there's a sense in which this is giving you j hat dot j hat is equal to 2, where the length of one of them is root 2. Okay? All right. Any questions? All right. Now, to make this point abundantly clear, there's another example I want you to consider, which is working in a non-orthogonal basis. Okay, so imagine we have two vectors, which are going to be our basis vectors, u1 and u2, where there's some angle between them. Just call it 45, just so you know it's not 0 or 90. Okay? Now, first and foremost, is Hunter here? Hunter?
No, Hunter's not here right now.
Hunter Solomon. Hunter Solomon's not here. Okay, yeah, I didn't think he's been here. Okay, guess who's next? It's Hunter. Shoot, I had so much fun that I forgot what I was going to ask you. You might get a freebie. No, I'm just kidding. I'm not going to give you a freebie. Oh yeah, is this basis linearly independent?
Yes.
Yeah, it is. In 2 dimensions, basically anything except for 2 collinear vectors is always going to be linearly independent. Is it orthogonal? Is this basis orthogonal? No, it's not. It's got a 45-degree angle. What angle has to be between an orthogonal set of vectors? 90, right? Okay. So this is not orthogonal. Now that doesn't mean we can't use the inner product. We can. Okay? But it looks like the following. So if x is AU1 plus BU2, and y is CU1 plus DU2, remember this is a linearly independent set, so you can take any vector and uniquely decompose it into a linear combination of this basis. Even though it's not orthogonal, you can do it because it's linearly independent. So here might be the two vectors, which are written as linear combinations of that basis. But now, if we want to take their inner product, what we get is AC U1 U1 plus AD U1 U2 plus BC U2 U1 plus BD U2 U2. All right? Where hopefully you all realize that unlike this nice clean scenario where we used an orthonormal basis, in this case, none of these are going to be 0. Okay? So this is one reason why using an orthonormal basis is so much better than using a at least orthogonal basis, if not orthonormal. Okay? So this one is not using a normalized basis, but it is orthogonal. This one is not using an orthogonal basis. And depending on whether this is 1 and this is 1 would tell us whether it's normalized. Okay? Now, it's time to turn to what we usually talk about when we want to abstract things, and that's go to function land. So, I will get rid of these examples because we don't need them on the board. So for case 5, consider P1, which is, of course, first order polynomials in a variable t. And we're going to take t to sit on the range from 0 to 1. alpha naught plus alpha 1t, and y to be beta naught plus beta 1t. Okay? Now, we might consider, okay, these are coefficients times basis vectors, right? So just like in the previous case, we might consider that the inner product of x and y just comes out to be alpha naught beta naught plus alpha 1 beta 1. Okay? Where remember, the 1 here, there's a 1 multiplying this, it's just a constant. And then the t, those are the bases. Okay, so we're actually working in a basis of 1 and t. Well, this is what I would expect if my basis was of what type? Drew? If it was orthonormal, exactly, because as I just brilliantly erased, if it was not orthogonal, we would have these cross terms. And if it was not normalized, we would have numbers here, giving the scaling, okay? But this looks like it's perfectly orthonormal. Okay, the cross terms are 0, and the scaling just gives you the number 1, okay? What do you think? Think that's true? Well, I have not told you how to find the length of the basis vector t. You might think I've given you a lesson for how to find the length of the basis vector 1, but t, what's the length of t? I mean, t goes from 0 to 1. Maybe it's 1. Okay? But if you even know the lengths, how do you know if they're orthogonal or not? Okay, so it's going to turn out that in this case, we're going to have to expand our definition of the inner product. And now is what you've probably been waiting. We're going to use the following definition. So let me just mark this out. We are going to use the following definition. xy is the integral from 0 to 1 of x star of t, y of t, dt, where the bounds on that integral are associated with the fact that t is defined between 0 and 1. Okay? Now let's apply this and see what we get. All right? So we can do this. Integral from 0 to 1, alpha naught plus alpha 1t. Everything's real in this. We can assume everything's real in this, so the star is not going to play a role. Beta naught plus beta 1t dt. And this is going to be alpha naught beta naught plus 1/2 alpha naught beta 1 plus 1/2 alpha 1 beta naught plus 1/3 alpha 1 beta 1. Okay? There are two things to note about this. In the 1t basis, so if we're working with this basis, notice that the inner product of the two basis vectors is the integral from 0 to 1 of t dt, which is of course 1/2. So our two basis vectors in this case are not, they're not orthogonal. Okay. Orthonormal is if we take a basis vector and do its inner product with itself and then see whether or not that's 1. But this is two different ones, and you're just finding that the result of the inner product between them is not 0, so therefore they're not orthogonal. Well, what about this expression also reflects that it's not orthogonal? I mean, this is the inner product of the two vectors.
Cross terms.
The cross terms, exactly. Remember from the examples which I eloquently erased? If you don't use an orthogonal basis, the inner product will introduce cross terms that are non-zero. And that's reflected here. Okay, make sense? All right. So, now, bear in mind, 1 and t is a linearly independent basis. You can use it to describe the vectors. It's just this inner product doesn't work out so nicely. Okay? Now, is there an orthonormal basis? Well, we'll start with orthogonal. Is there an orthogonal basis? It turns out that if we do 1 plus root 3t and 1 minus root 3t, then we have that the inner product of 1 plus 3 root t and 1 minus root 3t is 0. Literally, you can just take this function, multiply it by that function, do the integral over what's the result from 0 to 1, and you'll get 0. Okay, is this orthogonal? It is. It's ugly. It's got root 3's in it. But it's orthogonal. Okay? But you can do better still than that, because if we say 1 plus root 3t, 1 plus root 3t, this gives us 2 plus root 3. And that's for plus or minus. So we can instead use the set 1 plus root 3 over t, 2 plus root 3, and 1 minus root 3 t over, sorry, the square root over the square root of 2 plus root 3. And who can tell me what's so nice about this basis? It's orthonormal. I've normalized the basis vectors. Okay? So, if we express the vector, and I might call this u of t, and I might call this v of t. So if we express the vector x in terms of this basis, and I'm not saying that's going to be trivial, and the vector y in this basis, then what we know is that the inner product of those two vectors is just going to be alpha u, beta u, plus alpha v, beta v. Okay? That is, we know that since this is orthogonal, there will be no cross terms, and since it's normalized, there will be no coefficients, which are just basically rescaling or showing the scaling of the basis vectors. Okay? Now, there are other definitions of inner products which can be useful and which we will encounter. We could, first of all, change the limits on the integral to more general limits. This is, of course, going to be relevant for the inner product of functions. And we can also add a weighting function. So for example, we might have that the inner product of vectors x and y is the integral, and just go back to 0, 1 as our limits, of once again x star of t, y of t dt. But we might define the inner product to be inclusive of a function g of t. This is called a weighting function. Weighting, W-E-I-G-H-T versus W-A-I-T, a weighting function. Okay? And this is something which we'll encounter as well. All right? Notice, the g of t is sort of part of the definition of the inner product here. So even if I did like, you know, the inner product of u and v, it would still involve the same function g of t. It would just involve different vectors. Okay, so g of t goes with the definition of the inner product in a weighting function scenario. Okay? Oh wow. You look at the clock up there. All right. So So obviously, working with an orthonormal basis has, perks, and we're going to explore further perks associated with an orthonormal basis. Now, hopefully you've all worked with this definition of an inner product in terms of integrals of functions before, and you've worked with functional bases, so you've worked with Legendre polynomials and Fourier polynomials and all that stuff, right? At some point. Okay, we're going to formalize the treatment of that throughout the course, and hopefully we'll come to sort of an underlying structure which generates these various examples of vector spaces. All right, so let's go back to our definition, and I'll just get rid of this and then regret it immediately, as usual. All right. So here we go. In a finite dimensional space, vector space. An orthonormal set is complete if it is not contained on any larger orthonormal set. Okay. Now remember, when we were just talking about linearly independent vectors and we talked about whether they span the space, we had a different criteria, but this is a separate criteria that we can use when we have an inner product on the space and with these definitions of orthonormality. But this obviously makes sense, right? If we're in R3 and I give you the basis set x1, x2, they're orthogonal, and I can normalize them. I mean, technically I would call this I hat and j hat, but notation-wise we can be loose. Okay, is it complete? No, because there is an orthonormal set which contains this orthonormal set in R3. I mean, does that make sense? Okay. All right. Now, here's another result. An orthonormal set is automatically linearly independent though not the reverse of that. Hence, provides a basis and a complete one if so. Okay. So remember back when we defined the basis of a vector space as a set of linearly independent vectors, and then we talked about how to span the space, so it had to be complete. Any vector in the space had to be written as a linear combination of that set. Okay. Well, it turns out that an orthonormal set is automatically linearly independent. However, a linearly independent set is not automatically orthonormal. Okay, that's in my example from earlier. Linearly independent, not orthonormal. Orthonormal, always linearly independent. Okay? Now let's show this. So recall, if we have alpha sum over the components times the basis, if this equals 0, if this being 0 means that all of the coefficients are 0, then this means that the set of basis vectors are linearly independent. Okay, that was the old condition which we explored for finding a linearly independent set. All right? So what we can do is we can now consider, first and foremost, taking a basis vector and doing the inner product with 0. If I do the inner product with 0, then for I, what do I get? If I take the inner product of a basis vector with 0, what do I get?
That should be 0.
0, exactly. I'm only asking the easy questions for you guys. Hopefully, if I have a hard one, I'll prep you for it. Okay, now, let's suppose that this sum is 0. So we can write this as, whoops, stop that. So we can replace the 0 here by the sum over alpha I xi. Okay? Well, there's the linear structure of this that will allow me to bring out the sum over these simple scalars and leave the inner product of the vector x, whoops, sorry, this is xj, and that's common. The vector product of xj with xi, okay? But the vector product of xj, or the inner product of xj and xi, is just the delta function. So this is just going to give me alpha j oh, look at that. So I'm using the orthonormality of the basis here. This is just the orthonormality condition. But it's leading to this result that if this is 0, then this is 0, because alpha j is equal to 0. So we just proved this. That make sense? Okay. All right. Let me get rid of some of this. And we'll talk Bessel's inequality. If xi is a finite orthonormal set, in an inner product space, and x is any vector, then x squared is greater than, or the magnitude of x squared is greater than or equal to the sum over I, alpha I squared, where alpha I can be defined as the inner product of xi with the vector x. Okay. This is an orthonormal set, so if you have an expansion of x in terms of the basis, then you can pick off the coefficient just by taking the inner product of a basis vector with the full vector. You should be familiar with this from the dot product. Okay. Furthermore, the vector x prime, which is x minus the sum over j, alpha j xj, is orthonormal, or sorry, it's orthogonal to each xi. Okay. Wait, Shouldn't it be an equality?
Yes,
Yeah,
definitely.
but they call it Bessel's inequality. I mean, isn't an equality? Yeah, it's got that there. Why is this an inequality? Should I pick a card, or does somebody want to throw an idea out there?
Would there need to be a square root?
Say it again?
Would there need to be a square root?
No.
X doesn't have to fully span the.
Exactly. You're never told that this is a basis or that xi spans the space. Okay? That's the nature of this being an inequality. All right? So if we have an for an orthonormal basis, then we have x squared is equal to sum over I alpha I squared. Okay, for an orthonormal basis. But this is a set. This could be a subset of a basis, all right? So it might be that x, the vector itself, is written as the sum over alpha I xi, all right, plus the part that is not included in that basis, which might be j, beta j, yj. Okay? But this obviously immediately leads to x squared is larger than sum over I alpha I squared. Okay, so even if these bases are orthonormal, x squared is going to be larger than this squared because you got to add this to get x squared. Make sense? Okay. Now this guy is just what's playing the role here, right? So x prime is x minus sum over I alpha I xi. So literally move this to the other side, right? And then we can very quickly show that x prime, this guy right here, is orthogonal to all the other basis vectors. That is Anybody know why I wrote that there? This inner product just gives me delta ij, changing the j here to an I, reducing the sum to one term, making this xi, or alpha I, and of course the result of this is alpha I. They're orthogonal. Okay, we good? Okay. All right, so now we're going to lay out some conditions for completeness and then look at examples of them all. So how can we tell if our orthonormal set X is a complete basis of V? So X is a complete orthonormal basis of a vector space V if any of the following are true, and it can be any one of them. X is complete. That is, it's not contained in a larger set. if xix equals 0 for all I implies that x equals 0. X spans V, that is, according to the definition of spanning, which we gave earlier, every vector in V is a linear combination of the elements of X. Okay. I just want to give this, because, talking about spanning and completeness, they sound like the same damn thing, but we have different definitions. A complete orthonormal basis is one which is not contained in a larger orthonormal set. The spanning definition is such that every vector in the space is a linear combination of the set. Okay? For if X is on V, then X is the sum over I, xi, x, xi. 5, if X and Y are on V, then yx is the sum over I, y, xi, xi, x, which is called Parseval's equation. And then last but not least, if X is on V, then X squared is equal to the sum over I over alpha I squared. Okay? Now these are all things that can be proven, but if any one of them is true, then they're all true. We're not really going to prove, we're just going to go by example. Here we go. All right, so suppose that we had a basis x2, we had a basis x1, and that's it. This is in our set. But our set is going to be living in R3, so in principle, I could draw a third basis vector y, but our set is just going to be x1 and x2. And of course, we're going to use this as an example to show that the set I'm talking about is not an orthonormal basis. Okay, it's going to fail all of these. All right, so let's start with one. Well, first of all, x1 and x2 are contained on the set x1, x2, and x3 equaling y. So 1 is clearly not true. That's obvious, right? Okay. 2, y x1 equals 0, y x2 equals 0. I mean, sorry, maybe I should have specified this, but these are all right angles. So y x1 equals 0, y x2 equals 0, but y doesn't equal 0. Just showing that condition 2 is not satisfied. Okay. 4, 3, y does not equal alpha 1 x1 plus alpha 2 x2. It can't. There's no way you can express that third orthonormal vector as a linear combination of the things it's orthogonal to. Therefore, y does not equal x1 y times basis x1 x1 plus x2y times basis x2, which equals 0. And I mean, a lot of these look similar, but I'm going actually by what's here. So 4, okay, I'm showing that, well, actually, this linear combination of the basis vectors is 0 because these are orthogonal, but the vector y is not 0. Okay. And then 5, if we want to just draw an example vector, we'll call it b. Actually, no, I'm going to call it x for some stupid reason. But anyway. I'm going to try and do this exchange colors by hand trick. Okay. Oh, this is such a pain. I'm glad I'm having fun. Because I don't want you guys to feel left out. I'm fun at it. Okay. This equals 0. Because x1y is 0, x2y is 0. Well, wait, this doesn't equal 0. Because x and y are not orthogonal. Okay. And then for 6, Mateo, who do we remember for 6? Who do we remember for 6?
A person?
Yeah.
Is it? Bessel?
Yeah, it's Bessel. Remember Bessel? Remember Bessel? He said that this is normally an inequality because the set you're considering might not be complete. This is what you get if it's complete. But what we're arguing is that it's not complete. Okay, so Bessel. All right. Now we do have one more inequality, throw your way. And then we'll go on to the cranking machinery of generating an orthonormal basis, for better or worse. And this is Schwartz's inequality. Which says for vectors x and y, the magnitude of the inner product of the two vectors, and we're doing the magnitude because the inner product of two different vectors can be negative, or it can be 0, or it can be positive. The inner product of a vector with itself needs to be positive or 0 if the vector is 0. But if you're taking the inner product of two different vectors, you can get negative. So that's why I'm doing this absolute value. Is less than or equal to the magnitude of vector x times the magnitude of vector y. Okay? And so this is Schwartz's inequality. And to prove it, we can just say, all right, first of all, if y equals 0, then both sides are 0. Right? If y is 0, the inner product of 0 with anything is 0, and the magnitude of 0 is 0, so that's obviously satisfied. Okay? If y does not equal 0, then we can form y over the magnitude of y, which by itself, and this is the weirdest thing, is orthonormal. There's nothing around for it to be normal with, so we don't worry about that, but it's orthogonal. But if we're considering a one-dimensional subspace, it's orthonormal. Okay? Then we use Bessel's inequality. Can't forget the name of Bessel. To say, all right, the magnitude magnitude of x is greater than or equal to the magnitude of the inner product of this vector with x. That's just Bessel's inequality. But what can you do? What is this thing right here?
Scalar.
It's a scalar. I can just yank it out of here and in fact move it to this side. Whoops. There you go. Okay. All right. Are there any questions? All right, so you must have been wondering, and you've probably seen the answer before, but we'll go through it really quickly. All right, so you've sold me on the importance of an orthonormal basis that spans the space. Suppose I'm given some crap basis, like 1t, t squared, t cubed, t to the fourth, blah, 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 in a polynomial space. How can I find an orthonormal basis? Anyone know?
Schmidt decomposition?
Exactly. We're going to Gram-Schmidt the shit out of that. Okay? So let me just very quickly go through Gram-Schmitting. I know.
Do you know if we have class next Tuesday?
Say it again?
Do we have class next Tuesday?
Why wouldn't we?
There's a lot of classes are getting canceled for career fair. I don't know.
All right. Okay, first of all, you're graduate students in physics. I don't think you should be going to career fair yet. Your process of education will lead you into your career opportunities, but I don't know. If you want to go to career fair, I'll let you out of class. But I'm not canceling this class. We don't actually cancel Physics 100 because of career fair. It's really for like juniors and seniors, I think, in the undergraduate. But at any rate. All right. But I'm definitely not going to cancel for that. But thanks for asking and not just like skipping class and deciding, oh, I didn't ask. Okay, so here we go. All right. Now, I am not going to prove to you Gram-Schmidt. It's fine. You know, I'll give you a summary of it towards the end. It's a process more than something that needs proof. But I'm just going to walk you through an example. But the example I'm going to walk you through is our functional example, our favorite example. So we will apply this to P2, the space of second order polynomials. And we will start with what we can expect to be a non-orthonormal basis. Okay, where these are the basis vectors xi of the set X, all right? And do bear in mind that even though these are not orthonormal, they are linearly independent, so any vector in this space can be written as a linear combination of these. And in particular, that means that any orthonormal basis can be written as a linear combination of these. Okay? These span the space. We can write anything in terms of them. They're just not orthogonal. We can fix that. We can identify orthogonal bases, orthonormal bases actually, but they'll be expressed in terms of linear combinations of these. So let's go. Let's start with the simplest. We can always pick any of these vectors we want, and we can define it to be orthonormal. So we're going to take the x0 term of this, that's this guy, and we're going to divide it by its size. And this is going to be our basis vector 1. Okay, it's kind of straightforward. Now the work begins when we want to find a second basis vector. So then we can say, all right, well, y1 is going to be x1 minus alpha naught y naught over the magnitude of x1 minus alpha naught y naught. Okay? Where what this difference is doing is it's basically taking what we could imagine to be our second basis vector x1, but it's subtracting anything which is along this basis vector. Does that make sense? So the basis vector x1, that's t, okay, it might have some of this in it, so we're going to remove it by subtracting it. And then we're going to normalize by dividing by the size. Okay? Now we need to find what that coefficient alpha naught needs to be in order for this to work out. So we need, in order for this to go, we need y0, y1 equals to 0. That's the orthogonality condition which we want between this new basis. So we've got two vectors in the new basis so far, and we want them to be orthogonal. All right? So let's see this play out. 1 over the magnitude of x1 minus alpha naught y naught times 1x1 minus alpha naught 1 y naught equals 0. Okay. I could have put in a factor of x not there, but it's just 1. All right. Now let's just go through and evaluate what these are. So this is just x1. This is alpha naught, and this is 1. Okay, because the vector y0 is just 1, so the inner product of 1 with 1 is 1. Okay. So this tells us that x1 equals alpha naught. Okay. Everybody on board? It's pretty straightforward. Except there's a problem. You might spot it. Say it again?
Y1 is 0.
Yeah, so if alpha naught is x1, then this is alpha naught minus alpha naught times 1. So our second basis vector is 0. Does that make sense? Hell no. Where did we go wrong? Can anyone spot it? It's there. One of my cards. I'm shuffling them up. All right. That's wrong. What's the inner product of 1 with x1? Say it again.
0.
No, it's not 0. x1 is t, so
Yeah, 1/2.
1, yeah, exactly. It's 1/2. Okay. So at the end of the day, this should be 1/2, so alpha naught is 1/2. All right. And now we can actually write down what our first, or our second orthonormal vector is. So y1 ends up being t minus 1/2 over the magnitude of t minus 1/2, which ends up being root 12 t minus 1/2. Okay? could crank out y2 if we were in the mood. And I'll just give you the answer. Y2 ends up being x2 minus alpha naught y naught plus alpha 1 y1 over x2 minus alpha naught y naught plus alpha 1 y1. And in the end, after doing some work, which is shown in my notes, but I'm not going to crank through it for you, this ends up being square root of 180 t squared minus t plus 1/6. Okay. All right, so this is just a mechanism for generating an orthonormal basis from any given linearly independent basis. You will work a homework problem where you do this, so you can always resort to my notes. I'm not going to go into full-blown detail. There is another variation on the more general expressions, which is to say y1, your first choice is always going to be just the set, the element of the set that you pick. I don't have to pick x1, I can pick x2, I can pick x3, I can pick any one of them. But anyway, I'm just going to pick x1. That's divided by its magnitude. And then y2 is going to be x2 minus y1 x2 y1 over the magnitude of that. And then y3, et cetera, okay? And then what's nice is that for all of these, yi, yj is orthonormal. Okay, so I'm not going to go through the details of it, but in this situation, we're leaving in these unknowns, alpha naught, alpha 1, et cetera, and then we're using the conditions we want it to satisfy, this orthogonality condition, to find what the needed values of those coefficients are. So we're kind of treating them as unknowns in this construction. However, if you kind of do the construction for this case, and then you just kind of look at it and squint, you'll realize this is the structure that emerges. Okay? So to find the orthogonal basis, you don't have to treat these as unknowns. They're always going to come out to follow this pattern. So trust this if you want to build up an orthonormal basis. Don't go back and treat things as unknowns. Okay? Now one last tidbit before we depart, and that is, if you have an orthonormal basis, then it turns out that this gives you a means of figuring out the matrix elements of a linear transformation with respect to the basis. So remember, we got linear transformations, they're isomorphic to matrices acting on intervals. You might wonder, okay, if you have picked an orthonormal basis, does that make finding the elements of the matrix easier? Turns out it does. So let's very quickly go through an example of finding the elements of a matrix. Are there any questions on Gram-Schmidt? It's a calculationally intensive thing, but it's relatively straightforward in terms of its concept. Okay, so first of all, let's see how determining the matrix elements arises, and then we'll look at an example. So if we have a linear transformation on the vector xj, then we can always represent this as the sum over k of the elements of the linear transformation represented as a matrix over xk. All right, so this is the basis transformation. This is not the coefficients transformation. If I was doing the coefficients of the vector, I would do a, j, k, alpha, k, or a, k, j, alpha, j. But this is the basis, and the basis, you use the first index of the transformation matrix elements summed over the index on the basis. At any rate, that's something we pointed out a while ago. The result for the inner product is that xi a xj becomes xi sum over k a kj xk. And once again, we can use the linearity of the inner product to bring out the sum. And then we can use the orthonormality So to build the elements of the matrix A, we can just take the inner product as it stands between two basis vectors with A acting on it. A acting on the second. Okay. So let's see this in detail. So consider D on P1, an example of a vector space, which we're going to beat the crap out of. All right, and let's consider this non-orthonormal basis, 1 in T, okay? Where, as we're already familiar, the matrix D takes the form 0, 1, 0, 0. All right, and then we want to check this expression up here. That is, does xi dxj equal the elements of the matrix form of dij? Now, is this an orthonormal basis? No. Do we expect these to agree? No. Okay, this is good for an orthonormal basis. So I'm showing you the counterexample, and then I'll show you how it plays out for the orthonormal case. X1 is, it's the first basis vector, it's 1. dx1 is 0. Okay, well hey, that equals the first row and column element of D. So we do have agreement. Okay. Peeling right along, x1 is 1. dx2 is 1. Hey, that equals P1 too. Maybe this does work. X2 is, it's X1. X2 is T, dx1 is 0. The inner product of that is 0, and man, that equals tt1. I think this is going to work. X2 is t, dx2 is 1. That's equal to 1/2, which is not equal to d22. It failed. Let us instead do this with an orthonormal basis. If we Gram-Schmidted it, we'd find 1 and √3 2t minus 1 for the elements of an orthonormal basis. This isn't unique. So there's different ways to get different orthonormal bases. Like you could pick a different vector in the set to start with, and you can play the game. Okay, so there's many different ways to do it. All right, so let's check it out now. So with this basis, which is orthonormal, we have x1 dx1 equals, what's x1?
1.
What's dx1? 0. That equals 0. Okay. And then I won't ask you, I'll just fill in the story. So this tells us that our matrix has the form 0, 2, root 3, 0, 0. Let's check that. So D on alpha 1, x1 plus alpha 2, x2 is D on alpha 1 plus alpha 2 root 3 2t minus 1. I'm just using this basis for x1 and x2. Oh. That gives me alpha 2 root 3 2 x1, which means that my matrix needs to take alpha 1 alpha 2 to root 3 2 alpha 2 0, which is exactly what that bad boy will do. Okay. Any questions? All right, that's it for today. So tomorrow I'm going to have homework help hours from 1 to 3 and then 5 to 6. And your quiz will open up at 6 a.m. Thursday morning, and it covers the last week's homework assignments as usual. Okay. If you can't make the office hours, let me know. We'll try and figure something out. You can always email me questions, anything. Okay. I'm here to help you. And you're welcome to work together on the homework. I don't want you to feel like you have to work independently. That's one of the reasons I'm giving the quizzes, is to separately establish that you understand the homework. I don't care if you get to the answers together. I really don't. And I think that's beneficial for you to help each other. So feel free to work together on it. Any questions? Okay, and as usual, I'll update the homework tonight for next week's quiz. All right. See you guys.
We should rotate all the desks back so they don't use the same board.
That's actually very interesting.